I have good reasons to be happy to be here today, and I have also bad reasons to be unhappy to be here. I have good reasons to be happy because it's very nice of you to invite me again to give a lecture to your university. It has been a pleasure to be invited professor for more than 3 weeks in OPU. I enjoyed it very, very much. I have also bad, unfortunately, reasons to be unhappy, and these reasons are that I'm leaving in 2 days, and that's too bad because I like very much Japan, and I will be sad to have to go back, but that's how life is. So today I have decided to talk to you about the intramolecular carbonmetallation of alkynes. For those of you who followed my lecture 2 years ago, I am afraid that maybe you will remember part of the results, because at the time I presented preliminary data we had on this field. So now I'm just finishing the story and giving you the complete picture of the situation. So let's start now. Let's see a little bit, maybe I'll change that here. I'm sorry for the students that have suffered under my English in the previous weeks. And I'm still doing it in English because I had no time to learn Japanese in 3 weeks, but I will do better next time. All right, let's move. Let me explain why we embarked onto this chemistry. We were dealing for a long time with the chemistry of alpha-beta unsaturated acetals, which are quite interesting symptoms because you can do a lot of different chemistry with this type of compounds. And in particular, you can try to use butyllithium in CHF to do the deprotonation selectively of this position, which is quite acidic because in alpha of the oxygen and allylic. And you get, of course, delocalized anion here. And this undergoes relatively rapidly this fixation of the radioselectivity because of the intramolecular chelation, which fix Z double bond here. And then you get a beta elimination very easily. And so you get directly, in one step, the conversion of this acetal into this type of 1Z, 3E dienes, quantitatively with a almost full control of the 2 double bonds in one step. Very efficient reaction, very useful compound because you can do a lot of things with this type of dienes after that. So we did a lot of chemistry with that. For instance, we did some heterodyl-Zalder cycloaddition. I will not tell you more about that. It's just if you take this type of dialkoxydiene, 1,4-dialkoxydiene, and use these activated aldehydes, you can get directly this type of dihydropyranes. And you can see, of course, that these compounds are very close precursors to hexose. So it's a good way to make rare or modified sugars in a very, very quick manner, very efficient. So we published that a few years ago, but I'm not speaking about that today. What we tried to do with this kind of chemistry was to extend it from the double bond to the triple bond of an alkyne, because we were thinking of doing exactly the same kind of chemistry. So we did the same kind of reaction and did the deprotonation disposition. We probably went through this allene, and this allene underwent beta elimination, and we ended up with this cumulene, dialkoxycumulines. These are, of course, very strange compounds, 3 double bonds in a row with 2 alkoxy groups. They are very fragile, not easy to use, so we could not do very much with that, and unfortunately, we had to give up because the reactivity was very difficult to control. So we were a little bit disappointed, but before leaving the field, we saw that maybe we could do something else. Maybe using the same kind of starting material, instead of doing deprotonation, we could maybe do some nucleophilic addition on the triple bond. And if this was possible in a regioselective manner, we could obtain this kind of vinyl metal compound. And if a beta elimination was going on by elimination of the alkoxy metal here, we would end up with alkoxyallenes, and these are more useful compounds, much more stable and easier to use. So we thought maybe, let's see if this nucleophilic addition on the triple bond is possible. So we thought, well, let's try with a very simple case just to master the chemistry of these compounds. So we started this study with an intramolecular situation, intramolecular version. Why? Just because if we have a good link between the triple bond and the metal nucleophilic site, we could expect that the formation of this heterocycle here, if we have a Y here, this heterocycle would lead to the formation of this vinyl metal compound, and after beta elimination, we would end up with this type of exocyclic allenes that would be useful to prepare spiro heterocycles, and that would be a good way of preparing these compounds. So we thought, let's start with this case. That would be an interesting one. Of course, many questions arise. First, what type of cyclization can we expect on that? Will that be regioselective? Will it be N-exodig, as expected, or will it be a syn and anti or anti-carbomethylation of the triple bond? That's the first question. Second question is the elimination possible in this case? Can we expect the formation of this allene? And of course, what is the reactivity of these allenes? Maybe they are not reactive or too reactive, and maybe we cannot do anything with that. And of course, the obvious question is which metals? Which are the best metals to use in such a kind of situation? So let's see what we tried. There was some precedents in literature that were quite encouraging. One by Negishi did a very good work in 1990, published this interesting study in which it did this halogen lithium exchange, minus 78 degrees, and got this cyclization by carbomethylation of the triple bond very efficiently to obtain this type of indanes. Of course, in this case, the situation is favored because the resulting vinyl lithium here is stabilized by the presence of the silicon atom, and that favors greatly the cyclization. But not only this case was interesting, there was also some reports by Bailey a little bit later that showed that the intramolecular reaction of this terminal alkyl lithium on the triple bond was leading to the closing of these very strained four-membered rings with an exocyclic double bond. And you see in this case there was a methoxy group at the angular position here, and this beta elimination was indeed taking place to give rise to this exocyclic allene, exactly the one we were expecting. So it was very encouraging, albeit in the case of Bailey as well as Negishi, no hetero elements. So it's not heterocycles, only carbocycles. And there's also another example, interesting, by Krief, 2000, exactly the same kind as Bailey, with a benzyl lithium this time, carbocyclization on the triple bond, formation of the vinyl lithium, beta elimination, exocyclic allene on the 5-membered ring this time. So you see it's a variety of examples that were quite encouraging. So that's a carbanionic chemistry that was useful and maybe could be complementary of there's a review that has been recently published by Oshii on the carbomethylation of triple bonds. That kind of chemistry was looking very encouraging because it could be complementary of the cationic methodologies that you know very well in this country because of the work of Takeyama in Nagasaki University. Takeyama has shown that if you use the activation of these triple bonds by indium triflate, you can expect after deprotonation of this position a very good ring closing here with an exocyclic double bond in this position. So maybe the anionic version would be complementary of Takeyama sensei work.